You know, we rely on those glowing rectangles in our pockets literally every single day. We expect instant directions, real-time news, immediate texts to our friends, but how often do we actually look up and think about how it all works? Well, welcome to today's Explainer, because we are going on a journey into the invisible infrastructure orbiting high above us. We're going to completely demystify the satellite networks that, quite frankly, run the modern world.
All right, let's just dive right in. Imagine zooming way out into space to look at the anatomy of the incredible machines making all of this happen. Because before we can talk about what the network actually does, we kind of need to know what it's built from. If you open up the blueprint of a standard satellite, it looks incredibly complicated, I know, but it really just boils down to a few essential parts working in perfect harmony. Think of these four core components as the vital organs of every single piece of orbital tech. You've got the atomic clock, which is the beating heart of the whole system. And to put this into perspective, we are talking about precision down to a billionth of a second. If they were off by even a tiny fraction of that, your car's GPS would literally think you were parked in the middle of a lake. Then there's the transponder. This is basically the great communicator. It receives, boosts, and resends signals. You've got solar panels, acting as the power source, catching energy from the sun, and finally the propulsion system. These small engines act like a steering wheel, making absolutely sure the satellite stays locked in its exact orbit.
So here is our roadmap for this explainer. We just covered the hardware blueprint. Next, we're going to break down the three main pillars: GPS for locations, GIS for analyzing map data, and media communications for connecting the globe. Then at the end, we'll see how they all synthesize into a coordinated response.
Let's start with Pillar 1, GPS, finding our exact location.
So how does it actually find our exact coordinates? Whether you're in a car, on a flight, or just walking down the street, it uses a process called triangulation. Let's walk through the three critical steps. Step 1 is constant transmission. Multiple satellites are just constantly broadcasting their exact position and the time, completely dictated by those super precise atomic clocks we just talked about. Step 2 is the three-signal minimum. To get a lock on your exact location, your phone or sat-nav has to intercept signals from at least 3 different satellites at once. And Step 3 is calculating distance. The computer down here on the ground measures exactly how long each signal took to arrive. Picture those overlapping signals from the satellites, creating this sort of invisible geometrical net right over you. By figuring out the distance from each of those 3 points, your dashboard locks onto your exact location. And that is exactly how it can give you those seamless turn-by-turn directions. Now, obviously, this tech isn't magic, right? It's engineering. So we always have to weigh the incredible capabilities against the system's vulnerabilities. On the plus side, driving is way safer now. No more wrestling with giant paper maps on the steering wheel. We get real-time warnings for road closures and highly accurate arrival estimates. But look at the vulnerabilities. The local map databases can absolutely get out of date, and we've all been there. You can suffer a total signal loss the second you drive into a tunnel. Plus, it's totally dependent on the user. I mean, if you type in the wrong destination, the system is going to confidently guide you to a completely different state while you just blindly follow along.
Moving right along to Pillar 2, GIS, analyzing map data.
If GPS tells us where we are, GIS, or Geographic Information Systems, answers the much more complex question, what is around us? The biggest thing to grasp here is this concept of layering. Think of GIS like a giant stack of clear, transparent maps placed on top of each other. You start with a base map, then maybe you drop a layer on top showing state boundaries, then a layer of forest density, and maybe a layer showing pollution levels. By looking through all of these layers at the exact same time, computers can analyze how entirely different data sets interact in the physical world.
And this isn't just theory. The real-world stakes are huge here. For emergency services, GIS can instantly pinpoint the closest available ambulance to a traffic accident. In public health, this was absolutely vital during the COVID-19 pandemic for mapping the spread of the virus directly over population density layers. In the environment, biologists use it to track vulnerable animal migration patterns. And in law enforcement, it helps police identify geographic crime clusters so they know exactly where to deploy their resources.
Sure, GIS gives us borderline superpowers for analyzing complex data. But there's a catch. The software you need for this is highly specialized and, frankly, extremely expensive. Plus, there is a brutal learning curve. It takes operators a really long time to learn how to use it effectively, which naturally creates a barrier to who can actually access and leverage this incredible tool.
Which brings us to Pillar 3, Media Communications, connecting the globe.
You might be wondering, why even bother going all the way up to space just to send a message to someone on another continent? Well, laying physical cables across deep oceans or rugged mountain ranges is either insanely expensive or literally impossible. So space provides the ultimate shortcut. Satellites just bounce the signal right over the physical obstacles. So let's break down exactly how this orbital relay works. Step 1 is beaming up. A ground station sends an initial signal up into orbit. Step 2 is the satellite's job, and this is where it gets super clever. The onboard transponders receive that signal, they boost its strength, and crucially, they change its frequency. They have to shift the frequency, otherwise the outgoing message would collide with the incoming message. And finally, step 3 is beaming down. That strengthened, shifted signal is beamed safely back down to a brand new receiver on the ground.
Imagine that data actually making the journey. Up it goes from a dish, it gets completely transformed inside the satellite, and then boom, beamed safely back down to its new destination. It's this continuous, invisible dance of frequencies and data packets happening over our heads millions of times a day.
The biggest upside here? True global coverage. No matter the terrain, complete with high bandwidth and secure encrypted transmissions. But again, there are vulnerabilities. You've got latency. You know, that really annoying time delay you get on international voice calls. Plus, heavy rain and severe weather can totally mess with the signal. And perhaps wildest of all, these systems are vulnerable to solar activity. Actual sunspots and solar storms can disrupt transmissions out in space.
All right, let's bring it all together. The synthesis, a coordinated response.
Out in the real world, complex problems don't just use one of these tools. They require all three working in total sync. Think of it like a giant invisible matrix connecting the dots. Imagine an emergency vehicle desperately trying to navigate to a hospital during a major crisis.
Let's walk through how this actually saves lives in real time. First, health officials are using GIS to analyze data layers, allowing them to map out the outbreak and define the exact crisis zone. Next, let's say the local cell towers fail because of the emergency. Paramedics can just use satellite communications to bypass the damage entirely, securely transmitting encrypted patient data straight to the hospital. And all the while, the ambulance is relying on GPS to navigate turn by turn through unfamiliar streets right to the rescue site. The systems are completely intertwined.
So, bringing it back down to Earth, literally, we have to appreciate the sheer scale of what's happening over our heads right now. From atomic clocks in the freezing vacuum of space, calculating billions of a second, to layered data maps solving crises on the ground, this unseen network isn't just some neat convenience. It is absolutely the engine of the modern world. And that leaves us with a pretty wild thought to chew on. We've seen how robust yet vulnerable these orbital networks really are. If a simple sunspot or driving into a tunnel can disrupt this vital technology, how prepared are we for the day a massive solar storm goes way beyond just a minor disruption? With our modern world entirely dependent on this invisible infrastructure, what happens the day the sky goes completely silent? Thanks for joining me for this explainer. Keep looking up.